Okay, welcome back to another video lecture for calculus, and this video is designed to support a calculus course that I'm teaching this semester. And in this video, this is part 3 of section 1.4, we will be deriving the quotient rule, and we're going to be doing this in a very lazy way because in the previous video, part 2, we have proven the product rule, so we're just going to use the product rule in order to prove the quotient rule. Now, in order to do that, we're going to have to establish a small fact before we begin, and I'm not going to prove that fact in this video because we will do that when we look at the chain rule in a later section. So right now, again, it's kind of hand wavy. You're going to have to take my word for it that this is the way that this works, but we will prove it in a later video. And we are also going to look at how these quotient rules are just product rules in disguise. So there is another place where we have to use some extra caution when we're taking the derivatives of things, because in the first part of the 1.4 video series, we discussed the linearity property of derivatives, which means you can take the derivative piece by piece and then just put them together according to whatever the original function said, only if the functions of x involved in the original expression are combined in a linear way. When we got to part 2, we looked at the situation where we have two functions of x that are being multiplied together. So although the individual binomials in the example in that video were linearly combined, meaning with a plus or a minus, the binomials themselves were combined with a multiplication symbol. So the same goes for division because it is not a linear combination of functions. Here I have x squared minus 1 divided by x plus 2. It is not enough to take the derivative of the top and the derivative of the bottom and then just divide them. You remember when we did the product rule, we got a formula for it. We will get a similar formula for the quotient rule because it is not going to expand out the way that we would necessarily expect it to if it were a simpler function, because this is a composition of functions. So, first little thing we need to establish is that if we have a quotient such as this, where you have like an f of x on top and like a g of x on bottom, that's x squared minus 1 on top and x plus 2 on bottom, we can in fact write this in a way that can take advantage of the product rule. Namely, I can multiply the numerator by the reciprocal of what we see in the denominator, and that is equivalent to writing this fraction here. Now, the fact that this is a multiplication indicates that we are at liberty to use the product rule here, but for simplicity's sake and to try to make it more general, I'm going to make some substitutions again. So I've underlined in blue the x squared minus 1. This is the numerator term. We will call it u. And specifically, I'm going to take this x plus 2 and call it v. So I'm not taking 1 over x plus 2 and calling it v. I'm taking the x plus 2 and calling it v. This allows us to rewrite this expression as the derivative of u over v, which, by the breakdown that we did here, is the derivative of u times the reciprocal of v. So before we proceed any further with this quotient rule derivation, we do need to address the giant pink elephant in the room, which is, with the product rule, I do know 3 of the required 4 parts to come up with this derivative here. I know that I'm going to write this down times the derivative of this, which we do not know how to do yet. Then I'm going to write this down, which I know how to do, times the derivative of that, which I know how to do. So there are 3 things that we know how to do, and there's 1 that we don't know how to do. So what I'm going to do really, really quickly, I'm just going to give you this fact. This is in fact how this works, but we will prove this at a later date when we have discussed the chain rule. And what that fact is that when you try to take the derivative of something like 1 over v, you get is negative v prime, so negative of the derivative of that thing that's on the bottom, over v squared. And that just is what the derivative is. So we can apply that simple formula to our example problem if need be. And now we know how to write down what the product rule does to this derivative. So again, we have the first function, we have the second function, and we can now follow our product rule. Product rule says write the first function down times the derivative of the second function. That's the derivative of 1 over v, which I have given to you here. So that will be negative v prime over v squared. And again, remember that the v prime notation is just another way to say the derivative of v. Okay? Plus, then we write down the second function, 1 over v, times the derivative of u. And we know that the derivative of u, we can just write that as u prime. Okay, well there you have it. There's the quotient rule. That's the end of the video. No, I joked. This is, in fact, the correct formula for it. It's really not pretty, and in a way that we can like plug stuff in and get a nice easy result very quickly. So what I'm going to do is I'm actually going to combine a whole bunch of terms here. Notice that the left fraction can be written as negative v prime u over v squared plus u prime over v. But then I can also notice that if I simply multiply the right-hand fraction by v, then what I will get is a common denominator. That is negative v prime u over v squared plus u prime v over v squared. And then we can do some quick rearrangement here to arrive at what is commonly known as the quotient rule. That is u prime v minus v prime u over v squared. And again, like there was with the product rule 1d2 plus 2d1, there is a very common way that we say the quotient rule aloud that will help you remember what this formula actually is. If you recall, the v expression is the bottom term, the denominator term, the low term in the original fraction u over v right here. And the u term is the numerator term or the top term or the high term in the original fraction here. So a way that you can say this very quickly is low d high minus high d low over low squared. So if you were to read a textbook, you'll get a formula that looks like this. It just says you write down the derivative of the top term times the bottom term minus the derivative of the bottom term times the top term all over the bottom term squared. Or in other words, we can do the low term times the derivative of the high term minus the high term times the derivative of the low term over low squared. And it's very, very fast to say low d high minus high d low over low or over low squared, however it is you want to say that. Now that we know what this formula is, I can apply it to the original problem very quickly to come up with a derivative. And it should be noted here that this particular derivative is not a clean looking one. These are very, very, very nasty when you write them out to begin with according to this formula. They're very, very gross looking. And so there are some simplifications that have to happen if you want to make it look pretty, and just make sure that you're doing those algebraic steps very, very carefully so that you don't mess up what the entire derivative is. If you're unsure of it, you can leave it in its really ugly form, and it is a correct derivative, it's just not pretty. So now that we know this formula, which I will copy down to the top, I'm going to use the low d high version of it just to kind of help us out here a little bit. We know that this derivative follows low d high minus high d low over low squared. And in this case, what that tells us to do, to write out the answer for this thing, I'm going to, on bottom, put whatever the low term is, squared. Done. On the top of this fraction, I'm going to write 4 things just like we did with the product rule. But I'm going to write them in a particular order. First, I write the low term, x plus 2, times the derivative of the top term, which is 2x. Then I'm going to write the top term, x squared minus 1, times the derivative of the bottom term, which is just 1. And this thing here, this is a completely valid derivative that if you need to put that into the homework module, I believe it accepts it. But what we can do if we want to try to simplify this thing out for whatever reason, we can do the distributions that we see, giving us 2x squared plus 4x. We can distribute the negative symbol, ignore the multiplication by 1, that'll give us minus x squared plus 1, which will make the entire top term equal to 1x squared plus 4x plus 1 over x plus 2 all squared. And we notice that x squared plus 4x plus 1 will in fact have a negative discriminant, which just indicates that, oh no, I'm sorry, it does not. It does not factor. I was looking at a negative, I'm sorry. It does not factor nicely. And because it does not factor nicely, we really probably can't clean it up any better than that. So something like this would be our simplified form, and it's kind of a matter of preference whether you FOIL out the bottom or not. I don't, because it's just a binomial term with multiplicity, so it's sometimes easier to work with that way. But, important note, remember what you wrote here is in fact a valid derivative. As soon as you start doing these simplifications, if you do anything wrong, you can screw up your answer really, really fast. So if all you need is the derivative to plug some numbers in, then just stop there and start plugging your numbers in, because what you have is functional. It does work.